Okay, what we want to do is look at a problem involving the equilibrium conditions, both Newton's second law in linear form and Newton's second law in rotational form. What I'd like you to do is pause the video, give this problem a try to work it out, and then once you've either worked it out or you're not sure where to go, begin the video again. First thing, why don't you draw vectors on the plank representing the force of gravity on the plank. And of course, we're going to put that vector at the center of mass of the plank, assuming it's, and as stated in the problem, it is uniform. We'll denote it by force of sub P for force of Planck, and that's just the mass of the plank times gravity. The other force is the force of man, and that's given as 700 newtons. Draw the XY components of T1, and of course we show here T1Y and T1X. Now write down the equilibrium conditions. And of course that is the sum of Fx, all forces in the horizontal direction is equal to 0. The sum of Fy, or all forces in the vertical direction, is equal to 0. And the sum of torques is also equal to 0. What are the specific equilibrium conditions? Here we want to fill out for each one of the equilibrium conditions written in 4 the specific forces that go into those equations. For the forces in the horizontal direction, the sum of Fx, we have T3 acting in the minus x direction, so minus T3, plus T1x. Those two must sum to 0. Okay, go ahead and write down the sum of Fy, the forces in the y direction. And you have that T2 minus Fm, the force of the man on the plank, minus Fp, the force of the plank, plus T1x, which is the vertical component of T1, all must sum to 0. Now go ahead and write down the torque equations. Assuming the point as shown circled up here, and we can write it. And we have the sum of the torques will be equal to minus Fmd, the force of man, distance d from the point of rotation, minus the force of the plank, distance 1 meter from the rotation, where 1 meter is the point at which the center of gravity is located, plus T1y in the opposite direction times its distance 2 meters from the point of rotation. Of course, T2 and T3 do not act on the rod and produce any torque at that point of rotation. Now find T1y. Of course, I can find T1y by solving the torque equation. I know Fm, I know Fp, I know d, I know 1 meter, and of course we're at 2 meters, so plugging in the numbers, I get 322 newtons for T1y. Can you obtain T1x? If I know T1y and I know the angle at which the vector acts, can I get T1x? Yes, I can. It is just simply T1y over sine theta. 322 over sine 40 is 501 newtons. Now find T3. And of course, that's just 501 newtons. The magnitude is 501 newtons. Of course, T3 acts in the opposite direction of T1x. Find T2. Well, I can begin to add things up. 700 newtons for T2. We know what FM is. We know what FP is. I know what T1x is. So T2 is equal to 700 plus 294 minus 322. It would be 662 newtons. And a good example to look at would be example 12.2 in your text. End of module.